All right, so last time we started talking about the lateral load resisting systems, and I'm gonna go over them a little bit. So do you guys remember what is the first system that we have? Lateral load resisting systems. All right, so if you guys remember, we have two resisting systems, like gravity load resisting systems, which is the slab system with the beam system. And there's many types of them. There's solid slabs, flat slabs, waffle slabs, ribbed slabs, post tension slabs. There's lots of different slab types, and all of them to resist the gravity loads. If there's a lateral load is pushing on the building, this includes seismic, wind, even if you have a blast load. The blast load is like a pressure, like a pulse of pressures that hit the building right away. So that's an extreme load as well that can hit, lateral load that can hit the building. Also, sometimes water pressure is a lateral load pressure, but mainly when we design buildings, I mean like tall buildings, like the project that we have, we're gonna design them for wind loads and seismic loads. All right, so we said, do you guys remember what is the first system that we went over last time? Frame system. Frame system. And what does this system look like? It is something like this, columns and beams, and here's the base, and if there's an earthquake is hitting the building, and every time when I try to represent earthquake, I make something like this. A force at the base is hitting the building. Why? Because that's the difference between earthquake loads and wind loads. Wind loads is hitting the building from the surface, like the pressure hitting, but the earthquake is the soil is shaking, so it's always coming at the foundation, hitting the foundation like this. But if I want to represent a wind load, so I'm gonna make something like this, like something like this. This is hitting the building. So my building is gonna wanna move that way, like my building is gonna reshape that way, it's gonna make that movement. To resist that movement, these connections are gonna have, or the column is gonna have lots of bending moments. So I need to design these columns and beams and the joint between the columns and beam to resist this bending moment. This system is economical up to like maybe 30 stories. Okay, so that means it is not impossible to use this system in over 30 stories, but maybe it is not gonna be economical, okay? So you can design it, but you're gonna have lots of cross sections. So if you pick the other systems, maybe it's gonna be more economical. And do you guys remember when we talked about this system, we talked about the slope, right? We said that the slope of this system is big at the base, but when you go up, the slope is less. And we talked about the interstory drifts, and we said that this system is very good in the upper stories, and the lower stories is not that good. And we talked about the infilled frames. Infilled frames, so when you start to use like break walls, and we use this in the resisting system. So when this system wanna shift that way, it's gonna be struck on tie action inside the break walls, and it's gonna add more resistance to the building if you included the walls or the break walls to resist the lateral loads. All right, and number two, one of the main systems that we have is the shear wall system. The shear wall system is really good system. It's something like this, like a big shear wall. And the shear wall is an element that has one dimension is 5 times the other dimension or even more. So like maybe you have 10 feet length and maybe 1 or 2 feet width. So that's a really huge shear wall. Okay, so this shear wall, when it gets hit with an earthquake or a wind load, the deforming shape is gonna be something like this. It's something like fixed in the ground, and it's gonna make something like this. So that's the deforming shape. So the slope here is like almost 0, but here there's a lot of slope. So that system is really good down, and maybe it's not good in the upper stories. and this system is really good up to 60 stories, or I mean, like not good, I mean economical up to 60 stories. All right, so, and then we start talking, what if we did a mixed system, like number 3, we said frame, we said, what is the name of it, like combined frame shear wall, and we say sometimes frame shear wall interaction. Like you put the two systems together like this, and the frame is something like this. And it's usually, there's columns with the shear walls in the building, but usually the shear wall take a lot of load when the earthquake hit the building, because that's the strongest element in your building. And to enhance the interaction between them, sometimes we enhance this connection between them so we can make the loads transfer from the shear wall to the frame system. And this can make your system more economical because you didn't let the shear wall take all the lateral force, and you transferred some to the columns, and you made the columns to take moment, to take more of the straining actions. So it's all about, like, let's say that you are designing a building and you're having your building shear walls and columns, and there's 100-ton lateral forces hitting the building. So it's better to distribute the 100-ton between the frame and the column so that the cross section of the shear wall and the reinforcement of the shear wall can be less, so that you can decrease the cost. And at the same time, you make the columns and the frames take part of the load. All right, so that's for the combined system. And then we start talking about the outrigger system. So the outrigger system was something like this, and you have your shear wall like that, and there's the base, and we said we are gonna make a really deep beam and connect this beam with the column system in the building. And when an earthquake is gonna hit, or a lateral load is gonna hit, so what is gonna happen? This shear is gonna resist this lateral load, like this shear is gonna have a resistance like this, and there will be an extra moment coming from this column and this column. These two are gonna have, okay, the shear wall wanna go this way, but this outrigger, this cap, is making a counter force because the arm of the moment between these two columns. And let's say if this has 10 or maybe 100-ton reaction, this 100-ton is gonna multiply by the arm of moment that is really huge, the complete width of the building. So that's increasing the lateral resisting force of the system. And if you want to enhance this outrigger system, you make multiple things, like if you're building a 3D, you make, if you guys remember last time, there was a build around the building, like make the whole outrigger surrounding the whole story, and you make cross section, like you make outrigger distributed. So it's basically the whole story is gonna be an outrigger system. This story, we usually don't use it. We use it like for service, like you put maybe chillers for AC, mechanical equipment, stuff like that. Sometimes we need more than one outrigger. Sometimes maybe you need another outrigger here to enhance the performance of the system, okay? And we talked about this last time. All right, then we start talking about the frame, the tube system. Do you guys remember the frame tube system? So it's a frame system. Yeah, okay. So what we did last time, we said if we want to make the building very, very strong, and this is the top view of my building. I said that I use shear wall system, but the idea of using the entire perimeter of the building as a shear wall, like you make your building as a box, came up. Let's imagine that you have your building 60 meter by 60 meter, like 180 foot by 180 foot. And there is an earthquake is hitting that way. And that's the top view of the building. The building side view is something like this. And I'm looking from the top. All right, so, and you have two shear walls, and this shear wall is 60 meter and 60 meters. So you have 120 meter of shear wall length resisting this lateral load. So you are making your building very strong. But who's gonna live in a box? Like the thing is, if this is a shear wall, so there's no windows, there's nothing, it's gonna be really bad, okay? So it came the idea of how about if we're making some holes, all what we need from the outside is just some windows that we can see the light and do everything. So it came the idea that we can make a perforated shear wall, shear walls that has some holes, like this. Columns that are very closely spaced, something like this, all right? And they only have these openings for the windows, right? We make a very deep beam, like let's say we have a 3 meter story height, and you make the beam 1.2 meter depth, and you only lift with 1.8 meter as an opening. And the columns are very closely spaced, like you have 1 meter by 1 meter, maybe 1.5 and 1.5, and they have a spacing 1 meter in between them, or 2 meter in between them. So you are making it very, very close to a shear wall. So that's the idea of the tube system. But the thing is, I told you about the phenomena that it shows up here. When we use a perforated shear wall, it's called a shear lag, which decreases the performance of the building. Okay, so do you guys remember if we have a beam and all these are if I have a beam like this, and this beam has a specific push like that, and definitely it's gonna bend that way. And if I take a cross section here, and I wanna look at what's going on stress strain wise on this cross section. So, and this cross section have a bending moment like this. Where's the tension and where's the compression? Tension is down because that's the moment, and it's making compression on the top, right? So the stresses is gonna be something like this. It's gonna be this, and this one is making tension, so that's the weight. It's pulled the cross section, and this one is compressing the cross section, right? That's how it's looked like. Why the stress strain curve? Why the stress curve? This is sigma. Is a linear, because this cross section is solid. But what if this is a bridge section? A bridge section like a hollow section, like it's something like this. This thing is not gonna be linear. Maybe it's linear here, but if we look at the stress strain curve in a 3D, and this is the section that I'm looking at. So it's gonna be something like this, because this is a solid section. This is gonna be, the stress strain is gonna be something like this, in this section. And this is gonna be, the stress is gonna be something like that, and the stresses here is gonna be something like this. In here is gonna be something like that. What happened here? When you have this section wanna bend, okay? This is a solid, and the bending moment on this solid width is gonna be linear like this because it's a solid. But the thing is, when you have the stresses on this, on the top flange here, what is gonna happen? This section has like a web that is pulling this section up, and in the same time from the other hand, but this part is weak, doesn't have something to back it up from here. So like somebody's pulling from here and somebody's pulling from here, and in the middle there's nobody's pulling all the other section. So they are gonna try to pull it, like they are trying to stress the other parts, but not as much as on the corners. So there is a stress concentrations at the corners. But as more that is getting more stiff, like if this part is very stiff, like let's say the stiffness, we increase the stiffness of this part, make it very, very stiff, increase the material, make the stiffness infinity. If the stiffness of this part is infinity, so if you are gonna pull this part up and pull this part up, we're not gonna leaving this part. We either all go together or we stay together. So it depends on the stiffness of the flange, but definitely the flange stiffness is the same as the other section. So what happens is a shear lag over there. But in our case it's not a solid section. It's not even that way. Like it's not even all this is solid. It's like a bunch of columns that already have holes here. Like there's nothing here, there's nothing here. Like they're just like a bunch of columns here. So there is no concrete in the middle, and there is voids in between the cross section itself. So what is going to happen when this get an earthquake that way? The stress strain is going to be something. Okay, let me right here. Here is the building. Right? So what is going to happen? This part, like when an earthquake hit this building that way, is going to have a bending that way. So all the columns here are going to have tension. And the other side is going to have compression, right? Like this. The thing is, these two are going to have like the most stresses. Why? Because they have a lot of columns behind them and a lot of beams behind them that back them up to attract all the bending moment, attract all the stresses. But these ones in between them doesn't have the same thing that we have here. So this one is going to have also compression, but not the same level. And this one is the same. This one like this one like this. And when you draw the diagram, it's going to be something like that. Same thing on the side. This one is going to have some, and it's going to be something like if this is the linear between them, it's going to be something like this. And here it's going to be something like this. So that's how the shear lag look like. So in this side, if I want to draw it, it's going to be something like this. And in this side, if I want to draw it, let's say that this is going to be tension. So let's make it up. It's compression. And this is between them. So it's going to be something like this and something like this. And that's how the sides look like. And why is that so? Because when this gets load, like when this gets an earthquake load that way, this shear wall or this perforated shear wall and this perforated shear wall is gonna take most of the bending moment. But the ones, these are not gonna getting anything, okay? They are getting a little bit, but not as much as these two shear walls. If the earthquake is coming in the y direction, these two is the one that is gonna be active. But this one is gonna have most of the stresses, and this one is gonna have most of the stresses. But because this is not a solid shear wall, so it happened that way that the stresses here doesn't reach to come to this level. It only reached to that level. And how we bring it to the linear level, it needs that the beam between the two columns need to be very, very stiff so that they can come to be linear. All right, so it's about the tube system, and it's really, really huge problem, the shear lag problem. And I told you there's many ways that we can decrease the shear lag. You guys remember? We can increase the column cross section. We can increase the beam dimension, the spandrel beam dimension between these two. What else?
Increase distance between columns.
Yeah, the distance between columns, like decrease them. So all these can help with, but sometimes with all these in place, there's still huge deformation of the building. So sometimes we have to use other systems with this system. Like for example, sometimes after putting all the tube system and everything, there's still lots of forces. So I will end up using shear walls here in the middle. And like I have a core here and a core here, and I use it, and it's gonna be, let's say, like something like this. All right? So this tube, there's a tube outside, right? This core and this core, we can connect to them with something is called coupling beam, and this system it gets named tube and tube system. Why? Because there's a tube inside and there's a tube outside. But you will tell me, is this a tube? Yeah, this is actually a better tube than this, because you have a shear wall that is completely solid, doesn't have anything, you just have a coupling beam. But you'll tell me, but how this coupling beam is like completing the tube action between the two cores? That will take us to an interesting topic about the coupling beam. You guys heard about the coupling beams before? Actually, there's sections in the standards about the coupling beams, how to design them, how to reinforce them, so that these two walls, this one and this one, act as a one. Okay, so usually, sometimes in structural engineering, when you design buildings, sometimes you end up having like a wall like this and a wall like this, and they are separate. So everyone works separately. But if they are both of them one wall, they are gonna work better. That's actually what happens here. Like you have a column here and a column here. What we do in the tube system, we want the two columns, they work together so that they can have better bending moment. Rather than everyone has bending moment separately, no, you are gonna use the force here and the force here with the distance between them to create a big arm of moment to resist the external forces. And that's what happens when we talk about coupling beams. Let's imagine that you have a shear wall like this alone, okay? And then your design end up having another shear wall close to it, like something like this, all right? Two shear walls close to each other. And I'm gonna make this one more time. And another time. Okay. These two shear walls are very close to each other. You didn't connect them with anything. They are separate, and then they got hit with an earthquake or something, or a lateral force. Everyone is gonna resist the lateral load separately, right? Like this is the action. How's the action on the shear wall look like? And the stresses is gonna be something like this. This shear wall is gonna have tension here, compression here, and it's gonna act like that. And this shear wall is gonna have tension here, compression here, and this is how the stress strain curve for each one separate, right? Okay, so let's say that we connected them with a beam that is very strong. Like we start at each story, make a beam like this. This beam is strong enough to enhance this behavior. What is gonna happen is, but let's say it is not that strong. Like maybe, let's say it's like something in between very strong and there's no beam. And then here we couple them with a very strong beams. This one is very strong, the stiffness is very strong, this is like something in between. If the stiffness of this beam, let's say infinity, that means it's a very, very strong beam. These two walls are gonna act like a one single shear wall that is very strong, and actually the stress strain on this shear wall is gonna be something like this, as a one big stress strain curve. So what happens here, this is tension, this is compression, and that's the moment. This is tension, and this is compression, and that's the moment. But what happens here? There's a huge tension here, a huge compression here, and one big moment. So maybe the resisting bending moment of this system doubled or tripled this system. okay? How about one in between them? What happens exactly is, it's gonna be something like this. Like, once you connect them together, so when this 1.5 tension compression, like this beam is trying to have like tension compression, this beam doesn't allow it. If you want a compression, you need to compress me first before you compress yourself, okay? So what is gonna happen? You are gonna end up with having a system let's say it's gonna be something like this. So you are gonna end up with a system like this. All this is tension and all this is compression, and there is nothing here. Because there is nothing here. Okay? So all this is a tension and all this is a compression. So it depends on the stiffness of this beam, how much tension you are gonna have here and how much compression you are gonna have here. Sometimes you end up with like, if this beam is like not that strong, so you might have like this and just a little tension here, okay? So, or maybe it starts to be stronger, so you are gonna be having more tension and less compression, or it's not that stiff and you're gonna be something like this. So it depends on the stiffness of this beam, the distribution of the stress strain is gonna be different. So that's what we call coupling beam. That's why, if you guys remember, when we modeled the beam, we didn't make it as a frame. When we model it at the shear wall location, we make it as a spandrel. The same cross section of the shear wall, so that the ETABS can see it as a coupling beam, all right? And the reinforcement of this beam is like kind of different from the other beams. So what we usually do, we make like crossbars, like, let's make it, okay. So it's something like this, and this here is gonna be something like this. So that's how it's the reinforcement. It's like cross bars like this. And that's not only one bar, that's like a bunch of bars, maybe 5 or 6, depends on how much bending moment this shear wall is gonna have. All right, that's for the coupling beam. So that's what I can do here to complete the tube action, okay? All right, so is there any other systems that we need to learn about? Yeah, there's actually other way to decrease the shear lag. Right now we're learning the frame the tube system and how we make a tube in tube by making another shear wall in the middle. And there's something that's called the bundle the tubes. Okay, so let's say our building is like this, rectangle, and we said that the shear lag, what happens here, for example, it goes all the way down. But what if, like, did you see what happened in just one line? What if we make another shear wall here? I mean by shear wall, a perforated shear wall, like a bunch of columns very close to each other inside the building connected with very strong beam, and we made it another time. And same thing that way and that way. So it becomes a bundle of tubes. 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 tubes very adjacent to each other. That's what we have here, like, let's say 4 tubes here. Okay, so what happened is, if this system doesn't have tubes inside, so the shear lag is gonna be something like this. But that's actually if we don't have these tubes inside. But with these tubes inside, what's gonna happen? The thing is, you want to go all the way down, but then something very stiff stopped you, so you will go up. Like this. And then you wanna go down, and then something stopped you, and then you wanna go down, something stopped you, and then you go all the way down. So you decrease the shear lag from here to here. Just throw it, not good, so let me. Something like this. So you decrease the shear lag from here to here, and that's a very good way to decrease the shear lag in your system. Why? Because there's a very stiff element like a shear wall, increase the forces here. So it's become something like this. So what is the perfect? The perfect is like this has become a straight line. That's the perfect, if there's no shear lag. All the columns are taking the same straining action. That means is, if I have a column here meter by meter and like whatever, like 3 feet by 3 feet, and these columns are all the same dimension, that means that this column is working with full capacity, but the columns here are not working with a full capacity. Why? This column is getting this amount of forces, but this column is getting less forces, even though you are using the same cross section. So you have a column, same capacity like this one, but not working with the same efficiency, okay? All right, so that's what we call the bundled tube system. And actually there's a building that maybe you guys know in Chicago, it's the Willis Tower. It's like with this bundled tube system. How? They make the old bundles, it's like 9 tubes, and they make the tubes stop at different height. So not all the tubes are like until the top height. So they want to make it in a good shape. I'm gonna show it in the presentation a little bit, but I just wanted to show you how the shear lag looked like. Okay, so it's better to decrease the shear lag. So how can we determine the efficiency of the system? You come in the middle and you find out what is the amount of shear lag is. Like let's say you find that the forces here, the force here, like let's say it's 100. But if this system is act perfectly, it should take, for example, 200 as a reaction. I mean the reaction of the column. So that means that the shear lag is like 50% from here to here. It's like this is 100, so 100 over 200, so you have 50% shear lag, okay? So we measure in the middle and see how much shear lag that we have. The less the shear lag, the better. But you will tell me, okay, so how can I get this value? If you want to get actually the actual value, if this is a perfect system without any shear lag, let's say that this is our building, okay? And we put the earthquake load on the building, and we found out that this building is gonna have a moment M, okay? So if you have a moment M, if you guys remember, sigma equal M over I multiplied by Y, right? Do you guys remember this? If you wanna find the stress, you divide the bending moment over the stiffness and multiply it by Y. What is that? Like if you have, this is your building, and this is the columns that you have here. This is your tube system. No, you have like 300 columns or something. And if you want to find the stress at any point in your system, it's like a cross section, like this, and this cross section is having a bending moment like that. The thing is, if you guys remember from design, if you want to find the stress at any point, you get the I of this cross section, knowing the moment of this cross section, divide M, the moment on the cross section, divide M over I, and multiply it by Y, which is the location of the point that you want to get the stress at with respect to the CG. So, or with respect to the neutral axis. So if this is the neutral axis, so if you want to find the stress here, sigma at Y, so you divide M over I, which is, it's gonna be a constant value, and multiply by Y. The more the Y is, the more the stress is, okay? Same thing here. If you wanna find the stress at any point on this tube, so it's gonna be something like this. You need to find the total I of this whole system. And what do I mean by the total I? Like you get the inertia of all the columns with respect to the CG. So if you guys remember, you take this in dynamics and structural engineering. Like if you wanted the inertia of a column, I, it was, yeah, like let's say it has A and B, and you want to find the inertia about this axis. So it's gonna be B, A cubed over 12, yeah, right? And this is about this axis. But if you want to find about an axis here that is translated from here, so you want to find the inertia is going to be bigger or less? Bigger, right? So if you want, you find the moment of inertia about this axis and then multiply the area of this cross section by this distance squared, right? This is r. So it's gonna be plus the area multiplied by r squared, right? So what we are gonna do,
I'm just trying to remember.
oh yeah, that's like
I don't have
the inertia force. Like if you search it online, you will find it anyway. Like this is in many materials. You guys studied it in dynamics, studied in mechanics of materials. So yeah, and actually there's a lot of stuff. Like if you want to find this with respect to an inclined axis, there's a lot of things that you can do. But we are focused on the simple stuff. So if I want to find the inertia of all these columns about this line, so the thing is you need to find the inertia of this column with respect to this, and this column with respect to this, and the y keep increase, and all these columns with respect to here. So you're gonna get I1 here for, definitely if they are all the same dimension, so all of them has the same I, BA cube over 12. So all what's gonna change is the y. And then you will find for all of them, and then you will find the total inertia of the whole building. And if you have a shear wall, you need to find a way to get the inertia of the shear wall. You can divide it into small walls and then like deal with them as a column. So you already found I of the whole building and the moment of the entire building, so you get M over I, all right? And then you multiply the Y for each one, so you are gonna find the total stresses at any point. Like let's say you find I for the entire building and you already have the moment on your building, and now I wanna find the stress here. So you divide M over I multiplied by Y. So all this line have a specific stress. So you want to find it here, all this line have a specific stress level. So you'll end up like finding, if this is your building, so this is gonna be something, this line is gonna have a stress here, this is gonna be 0, this is gonna be compression, and it's gonna be linear like this. That's the linear one. Why? Because it's function in y. Okay? And same thing here, because all the buildings here are at the same y. So it's gonna be something like this, and this is gonna be something like this. That's how you find zero shear lag or perfect system look like. And this is gonna be a bonus in the project. If you try to find out what is the zero shear lag system or the perfect system and compare it with the lagged system and see how's the difference look like. You are gonna see how's your layout look like and then start to apply this rule for each building, and then you start getting the stress at each column, and you will end up having this linear behavior. And if you wanna plot both the lagged system with the perfect system, is gonna be, for example, something like this. So it's gonna be something like that. That is the lag system. Like you have tube system, and this is if actually the building is a solid concrete. What I mean by solid concrete, like a box. Like you build a tall building of a box of concrete, and this is like something that is not real, but this is how this building is gonna act like that way. Like you have a cross section of a beam. Okay. All right, so that's all about the tube system. So maybe I don't have to pull up the presentation. Let me see, maybe I will show you very quick. I'm not gonna record it because I just want to show you. So that's, I was showing you how's the perfect system look like and how the lagged system is gonna look like. So maybe make this just if we, since we don't record. And this is actually shows you how the shear lag is different from a story to another. Why? Because the way, when we go up, the compression force is like, when you go up, most of the forces is big down here, and once you go up, the forces is less. So the shear lag is gonna be less. So basically, when we draw a shear lag, we take a cross sections in all the columns at the story that we'll look at, and we'll look at the normal force in the columns. So if you check the normal force in this column, you'll find it that way. If you check the one after, it's gonna be this, until you come to the middle, and you will find that the normal force is that value, and then it's gonna go up as soon as you go to the other side. So, yeah, you know what? This two charts from my graduation project in 2013 back in Canada, because my project was a tube system. So I was trying to capture how the effect of the beam depths on the shear lag look like. So the beam depths has like, for example, decreased the shear lag from 10% to 9%. It's 1%, but it's still something. And it's a beam, not the columns, okay, and not the spacing. The spacing is the one that is gonna impact much more because you make all the columns are close to each other. And this one is the effect of the beam. Yeah, that's the shear lag and that's the drift. So like, for example, and when I mean drift, like it's how's the building displaced. And this actually shows you other systems that we can do to decrease the shear lag. So this is a tube system for a steel building. You have like the columns like this way, and there's a deep beam in between them, but also they put bracing around the building from the outside. Sometimes if the building is steel, we make bracing like this, and if it's concrete, you basically fill the hole at that story and make the bracing system. So that's also one way to do it. And if you see here, for example, like this building, like if you look at here, you will find that there's like a solid concrete or something, which means that it has outriggers. Like here, this building, can you see this area? Like not the same, that means that there's a solid section here, so there's an outrigger here, an outrigger here, an outrigger there, right? Yeah, that's actually was my graduation project back in the days. I was like having this tube system, like it was like a building in New York, and it was like a quarter of a circle, and there was a tube in the middle. And actually, we tried two different systems: one without inside tube, and one with tube in the middle. And this is how the columns were closely spaced, and actually was very, very challenging to capture the shear lag on this side because it's not a regular system. And this is a bundled tube systems, the one that building the Willis Tower or the Sears Tower, I don't know what they call it now, but this shows you if this is a one single tube, how the shear lag is gonna look like, and this is because it has multiple tubes, and this is how it shows the shear lag, like it goes down and then goes up. And so yeah, like it enhances the shear lag. But can you see this is almost aligned? Like the curve, you barely can see it. So that's for Sears Tower, and this is how actually the tower look like. And actually they make like a belt around it, and definitely maybe there's an outrigger inside as well. And there's a one here, and there's a one over there to enhance the tube action between the bundle tube system.
Is that usually where they have living space or just mechanical space?
They usually use that because the thing is you have like lots of deep beams inside, not only outside. There's inside connecting the whole thing. Like inside this one, there's a deep beam here and a deep beam there. So they make holes inside these beams to facilitate the movement, which definitely is going to impact the performance of the beam. But the thing is, you have to make these holes so people can move inside. So they use it like for chillers, they use it for mechanical, they use it for a lot of things. Sometimes they make it as a truss system. So they make like a big truss with the whole story, and they do that way. So yeah, that's actually most of the systems that are out there. So right now you are familiar with what systems that designers can use it out there. Sometimes you want to use a tube system, but the architecture doesn't let you because I can't put all these columns outside. So you have to use shear walls, even if it's not economical, but this is gonna serve for the shape of the building, so they have to pay what they don't care about money, they care about how the final product is gonna look like. Okay? So sometimes it's not about how economical your building should be, but it's about how the final product they want. So it's all things that you need to compromise. You compromise money for the final product. All right, so this will take us to a good point here, which is the class project, okay? So the class project is gonna be, let me actually record this. This is very important. So we have 13 students in this class, so I'm thinking about groups of 3 students, maximum 4. So each 3. What's going on here? I'm gonna restart my computer and then we talk a little bit about the class project. Yeah, we'll use this something there. Okay. So our project is gonna be a 60-story building, rectangular building. It's gonna be tube and tube system. I'm gonna provide you the layout. All of you are gonna have the same project, like 60-story, same dimension from the outside, but each one of you is it's gonna be what we call parametric study. So you're gonna have the same building. Some of you are gonna use a column dimensions of 1 meter by 1 meter. I'm gonna provide a table for each group. Some other are gonna use columns 1.5 by 1.5, and some of you are gonna use different beam dimensions. So depends on your group. So you are gonna end up using different dimensions. So it's the same project, but you are gonna model different things. Some of you are gonna have trusses. Some of you are gonna have outriggers. So I'm gonna tell this group is gonna do truss and outrigger. This group is gonna do this. This group is gonna do this. Okay. So I'm targeting 3 to 4 groups here. So and then I'm gonna send you. So maybe after this lecture, you guys try to decide which groups you are gonna be in. I don't want somebody to do the project on his own because it's gonna be a lot of work. So if 2 want to do it in their own, maybe, but I was hoping that at least 3 per group, because at the end, I believe when we present, we're gonna have 15-minute presentation per group. So I wanna be in 1 hour or in the 75 minutes during the class to finalize the presentation. The thing is, I'm gonna finish this part, like maybe Thursday I'm gonna talk about seismic analysis, so I will tell you how to apply seismic loads on your project. So, but the thing is, maybe I'll spend 1 or 2 lectures telling you how's the seismic load look like, what are the seismic loads, so that you understand what you are doing. And I believe we only are gonna do seismic, we're not gonna do wind loads. And once you are done, you are gonna apply your seismic load on maybe 10 models or 12 models, depends on your group size. So let's say that you are gonna try applying the loads on a building that is like has columns 1 meter. So the columns for each group, the columns dimension is gonna be constant. We'll see. Maybe you will change the columns dimension. But at the end, once you do your 12 models that has different columns dimensions and different beams dimensions with outriggers and without triggers, you are gonna end up with showing me graphs. For each system, X is gonna be system 1, 2, 3 up to 10. And 3, you will show me the shear lag, how the shear lag is getting less for each system or getting more for each system. How's the drift is gonna look like. So that's what we call parametric study. We're gonna see how a specific parameter impacts the system performance. When I say the system performance, we're talking about the shear lag, the inter-story drift, the total drift of the building. We are gonna look at all these separately, okay? The spacing between columns, yeah, this is the one that I'm not gonna change, the spacing between columns, because changing the spacing between columns, that means you have to redraw the building. But each group is gonna have different spacing. Like let's say this group is gonna have spacing between columns 1.5 meter. This group is 2 meter, this group is 2.5 meter. So everyone has different spacing. And then you all are gonna do the same thing. This group with this spacing is gonna change the column dimensions to these dimensions and the beam dimensions to these dimensions. Okay, so let me go on the AutoCAD file of the project here. I'm gonna share it with you today, but I hope after this lecture I get emails from group leaders, what the group names it is, and once you send me this, I will assign the class project to you. So right now the Zoom is showing here, it doesn't show on my screen.
You might have it as an external display instead of a project. Like
No, like it's
no?
like here showing, okay. Closed. Oh. So my screen doesn't show.
I think it was connected to another screen, so
What do you mean?
did you connect the laptop to another screen, so
I did the same thing what I do, like I put the HDMI,
Mm-hmm.
so
I need to, there's a function something to display which screen you are gonna show here.
no, it didn't show me that. Let's see. No.
If you go to settings on your computer and then display, you should have an option to either duplicate or expand.
So-
Yeah, it's probably just extending.
You said
Windows
split?
display?
Yeah, go settings and then
One
display.
or two?
So you wanna change so that it's duplicate instead of expand.
There's extend these, duplicate these, display. Okay, so it's done. Let's get back to Zoom. Did I upload the last lecture?
No, you don't.
So that's the layout of the tube system that we're gonna have. I'm gonna send it to you. It's a building. Dimensions are 63 by 63. But maybe some of you were gonna end up with like 64, 62. So the thing is, we wanna have, how many columns? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So we're gonna have like 22, 23 columns because let's say we're gonna have all of us 22 columns. So if some of you have the spacing 2 meter, they are gonna end up with like 22 by 2 is gonna be 44. Well, okay, let's make it 63, okay? If it's like 1 or 2 meter above that, that's fine. The thing is, we need to keep the spacing. I'm not looking, this is not a real project. This is just a practice project that we can do the parametric study to, okay? So you're gonna put your columns with the spacing that is assigned to you, and then you will find out. I believe here is the spacing from the center to center. And this one is like 3 meters, but from the side to side is like 2 meters because these columns, I believe, was like 1 by 1 or something. Yeah, that 1 by 1, so we'll end up having 2 meters between them. So the beam width, the beam length is 2 meters, and the beam depth is like 1.5 meters or something. So can you imagine the aspect ratio? All right, so that's how the project is gonna look like with beams all around. I will prepare this one to be sent to ETABS. Do you guys remember? We make the columns polygons, and then you can draw the beams and the slabs here, but from my perspective, I only like to make it easier for me, the most difficult thing is to draw the columns because there is hundreds of them. So I have to click one by one to do them. But the beams, just like 4 of them, so I can draw them in ETABS very easy. Slab is like 1 rectangle, that's it. So, and the same thing for walls. I can actually make a polyline and make the shear wall. So the shear walls is really huge. It's like, if this is 3 meters, so we have 12 meter by 12 meter shear walls. All right, so we have this. Try to make the shear wall, this wall, in the same line with the columns, these columns. It's gonna be much better than the way that I have it here. So maybe you make the shear walls on the same axis. Why? Because you're gonna build an outrigger system, and it's better to have the outrigger system cross columns and cross the shear walls, so it can work effectively. But if you wanna keep it like this, that's fine. All right, so let's say that you prepared your model and it's gonna be ready. Like, let's say, actually, I'm gonna copy this and move it to 0, 0. Actually, it's at 0, 0, so it's ready. So I can save as this building as TXF file or DWG file. So maybe I will go. Let's create a new folder. Keep it like this. I'm gonna keep it DWG. I'm gonna say save. And I will go to ETABS. And if you guys remember, we're gonna do file, new model, and then I'm gonna pick the units. I'm gonna make it metric. I'm gonna say okay. I'm gonna pick blank, no grids, because I already have the drawings. You start define your sections, your materials, and your everything, and make the model that is ready to assign the cross sections. So what if I would do it, I would define the slab thickness, the material, shear wall thickness and materials. And by the way, the shear walls here is gonna be 1 meter or maybe 1.2 meter width, okay? Because that's a big building, that's 30 centimeters or something. And this is also one of the things that we're gonna study. If you change it, the thickness of the walls. Okay, so what I'm gonna do, I'm gonna go to File and hit Import, and then I will go to DWG Architecture Plan. And I'm gonna go back here, Class Project, and I'm gonna change this to DWG. Make this file. Let's see if it's gonna bring it, because we have it open on AutoCAD. So I'm not sure if we need to close AutoCAD. I'm gonna bring this one at Story 1, and I'm not gonna do any scaling factors. I'm gonna hit OK. Let's see if it's gonna bring it or not. I believe if it's WG is okay, but if it's DXF, you have to close AutoCAD. There's lots of details. So it says importing elements from DWG file. Should have imported before it comes here. So once you import the file, it was gonna bring all the layers, the columns layers, the walls layers. So do you guys remember we went to the layer itself and said add column object, add beam object, add wall object, and it adds everything. So once I do it, and make the versus story, okay, say scans at the end. Alright, let's close this and try one more time. If it didn't work with DWG, we're gonna try DXF file. Actually, try something.